Hello everyone. So welcome to the eighth week interaction session for the course on control systems. So my name is Soumya and I am a PMRF fellow at IIT Gandhinagar. So last time we had several problems on root locus. This time we might have a question on root locus, that also not root locus in detail, but rather we are shifting our domain towards frequency response kind of thing, and some very general questions. Like you might have seen in the lecture that there is some case study related to root locus and you're supposed to find out some related to frequency response. So we'll be covering all sort of things. So basically whatever questions are going to be there are really a brush up of all the concepts that you have learned till today, be it your damping of the system or Rauther stability criteria or root locus. So all sort of things. And then we are also going to see this state space representation of a system. So till now what we are doing is we were generally going into Laplace domain to solve our problem. But what if we can represent our system in the form of some metrics, and we can derive some sort of behavior from there. Like if we have some metrics for input, some metrics for output, some metrics that determines how the states will progress over time. So all sort of things are covered in state space representation. So we'll see them also. So let's start with the lecture. The first question is really an easy question. So it says that the open loop transfer function mind it, this is open loop only, of a negative feedback system is given by this, where k is a non-negative real valued parameter, means k is greater than 0. Okay, then the closed loop system is stable for only what? So how we will find that when is the closed loop system going to be stable? Now there are multiple ways in which we have learned. As of now, we know that if we determine using the Rauther stability criteria that do all the poles lie in the left half of the S-plane, we can answer something from there. The other way we learned is that if we plot the root locus, and if the root locus goes in the right half of the S-plane, because the root locus essentially gives you the behavior of closed loop poles. So if it moves in the right half of the S-plane, you would be able to know that, okay, this system is not going to behave in stable situation for such and such values of k. So both these methods you have learned. We would have other methods again. After this week also you are going to have some other methods. We will see them later, but let's say, so there are two methods, right? As of now, Routh-Hurwitz, where we use the characteristic polynomial. Other method is root locus. Now you see the order of the system, it is just a second order system. In the denominator you have a second order system only. If you have this, it is very easier to go with Routh-Hurwitz criteria, because you need not even construct a table. So the two conditions would be sufficient. So how do we do this? So let's so you know this, that open loop transfer function is k upon s square plus 4s. What is closed loop transfer function? This is gs, right? Since in the question there is no mentioning of what is hs, if it is unity or non-unity, whatever, nothing is mentioned. So in that case we assume that hs is 1. All right, so your closed loop transfer function is given by gs into hs upon 1 plus gs hs. Why plus here? Plus is here because it is a negative feedback closed loop system. All right, because of negative it is plus. If it were positive it would have been minus. Now when you try to find this,
Madam,
yeah,
it is open loop transfer function, no madam. G of s h of s is equal to k by s square plus 4s, madam.
G,
Then the
right?
characteristic, G of s h of s,
Yeah, yeah,
then the characteristic equation is 1 plus, right madam?
yeah,
1 plus k by s square plus 4s madam.
yeah, yeah. There
Like
only
that
I'm
only.
coming. I'm coming to that
There is
part.
no need of a closed loop transfer function, no madam. It
Yes,
is
yes,
g
yes.
of s
You
by
can.
1 plus.
So what I'm really doing is now. So I'll tell you. Just let me write one more sentence, then I'll tell you. K upon s square plus 4s plus k. Am I right? Yeah, I'm right. So this is your. So why I have written is this to let to just like uh, emphasize on the fact that this is the characteristic equation. So you already know that this is the characteristic equation. This equal to 0 is the characteristic equation. But I have written to just make sure again that this is the characteristic equation. That's it. All you have to do is with this only. Nothing related to numerator. That's why. Now, when you have, so from here you can see characteristic equation to be s square plus 4s plus k. What did, what is Hurwitz polynomial? Or how do we say that this is Hurwitz polynomial? So there were two conditions, right? So the coefficient of s square, s and s to the power 0 should be non-zero. That means k is definitely not going to be 0. All right. The second condition was that the coefficient of all the powers of s should have the same sign, no different signs. So for s square, the coefficient is 1. For s, the coefficient is 4. For s to the power 0, the coefficient is k. That means k should also be greater than 0, since all of them are greater than 0. So k should not be equal to 0 and k is greater than 0. That only means that k should be greater than 0 for the system to be stable. So your answer is this. Okay. Okay. We'll move to the next question. So from the first question only, it is desired that the closed loop system obtained in problem 1. So your, so that is why also I wrote this closed loop system. This will be using this again and again. This was your closed loop system. Okay. So it is desired that a closed loop system obtained in problem 1 be an underdamped second order system. So what is underdamped second order system? What is underdamped system? Essentially, you have to tell me what is the value of zeta over here. Or let's revise this because,
Less than 1.
right, less than 1. So there are 4 categories. I would start from the very first category only. Wait. Undamped system where zeta is equal to 0. There is no damping. Okay. Underdamped system which has zeta in between 0 and 1. Critically damped system where zeta is equal to 1. Overdamped system where zeta is greater than 1. Okay. We also saw the graphs in the earlier lectures. So the question says that this system should be an underdamped system. So for what values of k it is going to be an underdamped system. So how are we going to answer? So we already learned that this closed loop transfer function, which is given by 4s plus k in this case is equivalent to omega n square plus s square plus zeta omega ns plus omega n square. So this is the closed loop transfer function for standard second order system. From here, you can say that omega n is under root k. Then you have to compare 2 zeta omega n is equal to 4. That means zeta omega n is equal to 2. That means your zeta is equal to 2 upon under root k. So what do we want? Uh, for underdamped system. So for underdamped system, it means that zeta should be less than 1. That means 2 upon root k should be less than 1. That means k should be greater than 4. Do you have it in the option? Yes. K should be greater than 4. I hope this is clear. So you just have to compare both of these equations. Whatever you got from the system and whatever is the standard second order system closed loop transfer function. And then you're supposed to compare and find out the results. Okay. You'll be revising the concepts today a lot. Okay. What is true about the underdamped second order system? See, the question is already saying underdamped. So for sure, when you had underdamped here, we said that k should be greater than 4. So this is a constraint already there. Now we'll proceed later. So second order system identified in problem 2. What is true? The questions are about the settling time. So let's find out the settling time. So what is settling time? We will solve this for k is equal to 4 to get the boundary condition. Now what is settling time? There were two definitions for settling time. One for 2% band, one for 5% band. What was it? And we'll be answering the question according to this. So what was the 2% and 5% band? You should remember this.
40, madam.
Sorry?
40. Time
40.
constant T. Yes, madam.
Oh, no, I don't want in terms of time constant. Rather, I want in terms of zeta and omega n. Because the question we are solving
4 by
is
zeta omega n, madam.
for what? For 2% or
4,
5%?
2%, madam.
Right,
4 by zeta omega n.
right, right. And this is,
Zeta omega n is equal to 2.
yeah. So 4 upon zeta omega n, which is the settling time in our case. Zeta is zeta, yeah,
Zeta omega n is 2, madam.
yeah, zeta omega n is 2. And then because you have
C.
root k, which you can cancel, so this will be 2. So it should have a settling time less than 4 seconds. All right, I hope it is clear. Okay. So the next question is, again, the question is related to underdamped system. So k is greater than 4. Have maximum peak overshoot less than 10%. I want you to solve this problem uh, because,
If you don't mind once, could you please scroll up?
okay, yeah.
Okay, ma'am. Thank you.
in the fourth question, we are supposed to have a peak overshoot of less than 10%. So there was a formula for maximum peak overshoot. It was just in form of zeta. So when we had done this maximum peak overshoot problem, there was something that if you have more overshoot, that means the system has less damping. If you have more damping, there would be less peak overshoot. How we had seen this? There was an example for like slamming of the door. So if the door overshoots to the other side to a large extent, that means that it is underdamped. If it does not, if it goes slowly and it gets to its original position without overshooting, that means that it has higher zeta value, higher damping ratio value. Now, maximum peak overshoot can be defined as, uh, please solve this question. This is highly numerical and it would help you because you'll have such questions in assignments, in exams everywhere. 1 minus zeta square. So this should be less than 10%. So if we are going to solve this question, how we are going to solve? So we are definitely going to take ln. If you take ln on both sides, so it would be uh, minus zeta pi upon under root 1 minus zeta square to be less than ln of 0.1. Okay. Then you can go on solving this. You'll also see or we can take the other way also. Before taking log, I will take you through the other steps, but you can go in all the steps. So let's say I want to remove this minus sign. Zeta pi upon 1 minus zeta square should be greater than 10, right? I have just flipped the numerator and denominator with the change in sign. Then zeta pi upon 1 minus zeta square. Now I have taken ln 10. What is the value of ln 10?
2.302, ma'am.
Yeah. Under 1 minus theta square is equal. Let's take it to be 2.3 only. So once you take this value, then you can write you will have to square on both the sides, right? So it would be zeta square 2.3 square into 1 minus zeta square. Then from here, you'll be able to solve from here. It is very easy to solve. So you can tell me the final value of zeta. And we have to select an option from here. Sorry, just a second. Why is this connection lost? Yeah. From here, you have to calculate the value of zeta. These four options are given to you. Mind it that there is already a constraint that k has to be greater than 4 because of underdamped second order system. From here also you're going to get something. Rather, you should have Zeta would be greater than some quantity. What is this quantity? Has anyone got the answer? It's very simple now. You just have to find out the value of zeta.
Theta value 0.58 ma'am.
0.58, right? Very good. 0.58. So from here we can say that zeta should be greater than 0.58. So we want to say, so zeta was what? It was 2 upon root k. Should be greater than 0.58. Then from here you're supposed to find out how we'll relate it with k. So 2 upon 0.58 is greater than root k. So k should be less than 4 upon 0.58 square. So you'll find that k should be less than approximately 11.4. Okay, you'll get this answer. 11.4. So which option is correct? So we already had this condition that k should be greater than 4. And from here we have got k should be less than 11.4. So your answer is option A. Okay. Do expect this type of questions everywhere where you're supposed to relate, find some relation between some performance specifications, like you have rise time, settling time, maximum peak overshoot with, so all of these you know very well are dependent on zeta or omega n. So you might have some transfer function given from where you're supposed to determine what is zeta, what is omega n, and then you try to plug it in the formula for maximum peak overshoot or settling time or rise time, and then you try to evaluate those parameters. So this is sort of important question. Okay. Okay. So which of the following statement is true about the locus of closed loop poles? So I'll take this again. I might have this already. Yeah. So this was your closed loop transfer function. Okay. So which one of the following statements is true about the locus of closed loop poles? Now there are two ways again to do this. One is, since the question is all about root locus, what you'll do? You'll plot the root locus. But the question is only asking if it is going to be in right half or left half, whatever. So why should we plot the root locus? It is not at all needed. What we can do is, we can just check RH criteria. See, if from here, if you get the poles to be in the right half of the S plane, that means the system is already unstable and you have a root locus in the right half of the S plane. So you get your answer from here directly. So if the question does not ask you to draw the root locus, there is no need to do so. You may draw, you may find out, does it ever go in the right half? Then you can have the answer. Or the other way is check RH criteria. From the RH criteria, for the given value of k, if you get that the poles are in the right half of the S-plane from the characteristic equation, then you'll be able to say that, yeah, my root locus would go in the right half of the S-plane. Okay. So from here, yeah. So what is your characteristic equation? S square plus 4s plus k is equal to 0. All the options are for k greater than 0. So we have to look only k greater than 0. Now if the coefficient here is positive, coefficient here is also positive, then this coefficient should also be positive. Okay. For stability, it should be positive, right? And we see that all the options have k greater than 0 as option only. So definitely we are going to have stability only for all the options. So if it is stable, what could be the answer? The root locus always lie in the left half of the S-plane, not in left and right, because there is no uh, closed loop pole in LHP and RHP, because you can see this from Hurwitz polynomial itself. The root locus lies always on the real axis. Yeah, this you can check that if it always lies on the real axis or not. It could be one of the, or it always lies on the imaginary axis. So these two options are worth checking. And how will you check this? From here you got that it would lie in the left half of the S-plane. Unfortunately, you had this in the first option itself. So you could say that, yeah, it lies in the left half of the S-plane. But if you want to check that it lies on real axis, it lies on imaginary axis, then what you'll do? Then also it is very easy, no? It is just the first step of root locus only. That you find where are the poles, where are the zeros, and then find that if it is going to be the same thing, that this part lies and no other parts are going to lie. There are no asymptotes, there are no closed loop poles. If nothing is there, then it would lie on the real axis or imaginary axis. But in this case, if you will try to do that, you'll get the answer like in 1 minute or not even 1 minute, 30 seconds only. That no, it is not going to have both of these options. So try constructing the first step if you're given such options where it is real axis and imaginary axis. Else from the first option only we get the answer that it always lies in the left half of the S-plane. Okay. Okay. So
Ma'am,
when select,
how to know whether it's
so,
in the imaginary axis?
you have to find the intersection point with the imaginary axis, like crossover point or something. If you are able to find that, then only you'll be able to say that if it is on the imaginary axis or not. So,
Yes, ma'am.
so crossover point would come. So if you don't get any of these options, then you're supposed to find this. So it would be somewhat long step, but you'll get that. You will be able to understand already that let's say I have these many poles, I have these many zeros, this would terminate to this point. So if it is even going to cross the imaginary axis, or it is not going to just cross, it is going to lie on the imaginary axis. So some sort of intuition that you have built from all the question solving will help you here.
Okay, ma'am.
Okay. Yeah. Okay, so let's proceed with the next question. This is state space representation. Why do I have this color? Yeah. So yeah, this was the mass spring damper system that we had done like much back. So you already know that a transfer function is this for a spring mass damper system. But this is a Laplace domain. So this is your transfer function in Laplace domain. Now, if there is a way in which we can write the differential equation, so this was your differential equation, right? This one. If I can write this differential equation in some sort of way that we can write it as n first order ODEs. So let's say if the order of my system is 2, then can I write, and it is a differential equation of order 2. Is there a way in which I can write two equations, two first order differential equations, so that we have simplified solution? Can we represent it in some sort of matrices and as n first order ODEs? So that is the way we represent our system in state space representation form. So when you do this, you're going to deal with state variables. So yeah, state variables are those variables whose knowledge at each and every instant of time is sufficient to completely characterize the system. So let's say, I don't know which background you all are from, but let's say we have some electrical system in which we have, let's say, an input source. Okay, I'll draw it here. Some input source. And then you have some resistor over here. Then you have, let's say, a capacitor over here. So this is a series RLC circuit, RC circuit. This is your input. This is already known. This is R. This is C. Okay. What all system variables would help you completely characterize the system? Like, if I want to know some quantities which you have at any point of time, which is accessible to you at any point of time, then would you be able to say what is happening in the system? Nothing would remain unknown. So is there a way?
Current through the circuit and voltage across the capacitor, madam.
Right. So if you have the current here, let's say I call it IR, or I would just say I, and the voltage across this capacitor, which is VC, then these are the terms which were only unknown in the system. If there is some way in which I can find out what is I and what is VC, then I'll be able to say, okay, what is going in my system? I would be able to say what is the current which is flowing in the circuit, what is the voltage across the capacitor, and everything. If any one of them is absent, the information will be incomplete for the system. So the number of variables which are necessary at every instant of time to completely characterize the system. Okay. Now, okay, these are the questions that we'll see. So this is one way of representing the mass spring damper system only. So this is the way in which it is represented with these sort of equations. So in general, what happens is, this is important, you'll be able to represent your states of the system. It can be x1, x2, x3, whatever number of states. So how many states you'll have for the system? You will have the number of states for the system would depend on what is the order of your system. If the order of the system is going to be 2, then you're going to have 2 state variables over there. So, and you can define the output also in this way. We'll see the questions now. But in general, what you have to remember is, you will be representing some sort of differential equation in this form, axt plus but, and your output would be related to your state variables as cxt plus dut, where your a would be, I don't know, it should be written somewhere. Okay, no problem. A would be your system matrix, B would be your input matrix. Why input matrix? Because it is related to the input of the system. C is your output matrix. So here in this equation, x is your state variable that defines the system. U is the input that is given to the system. In the last example, it was V in, and yt is the output of the system that you want to derive. Let's say you want to say that, okay, my state variables are current and voltage, but I just want to find out what is the current of the system throughout. So you would say that, okay, my yt is going to be the current which is going through the circuit. So we'll represent it in that way. We'll have the questions now, but essentially what is important is this. Remember this: x dot t is equal to axt plus but, yt is cxt plus dut. We'll be mostly finding out all the matrices a, b, c, and d and giving the answers. Okay, now see. Okay, okay, let's say so this is a CISO LTI causal dynamic system. It is given by both of these equations. If we want to find out some relation between ys upon us, how we'll be able to do? So you see here ys is related to us in Laplace domain. Here xs is related to us. Now xs is also present here with ys. So definitely solving these both equations will give me some relation between ys and us. So that is what is taught here. That let's take the Laplace transform of the first equation. So when you take the Laplace transform of this equation, you get this, where s into xs minus x0, because we take the initial condition, is equal to axs plus bus. Simply Laplace transform. Taking the initial conditions to be 0, this would remain, right? Once you have this, what you'll do? You'll take x on one side. Now, when you take x on one side, A is a matrix. S is just a variable, Laplace variable. So definitely you cannot perform subtraction between a variable and a matrix, A matrix. There has to be some matrix operation over there. So this S is multiplied by identity matrix. So Si minus A into Xs is going to be equal to Bus. So from here you have got some sort of relation. So when this is there, so you can write xs to be equal to Si minus A inverse, because when what you can do here, so you will multiply this by Si minus A inverse on this side, and here also you will multiply Si minus A inverse, right? Here you'll get identity matrix from both of these, and here this would remain. So your xs is equal to Si minus A inverse into B into Us. Okay. Since you have got this, now what we'll do is, अभी एक्सेस और यूएस के बीच में क्लियर रिलेशन मिल गया है, जिसमें एक्सेस इज समथिंग डिफरेंट, यूएस इज समथिंग डिफरेंट, एंड यू हैव सम रिलेशन इन बिटवीन. नाउ ys is equal to cxs plus dus. So let's replace the value of xs over here. So c into this xs comes over here plus dus. So what happens here? You see you have common us in both the terms now, and ys is here. So you can write ys is equal to this complete term into us. So this ps is ys upon us. So from this whole derivation, you have been able to find out what is the relation between output and input of the system in terms of some matrices, some manipulation of the different matrices, system matrix, input matrix, output matrix, these the coupling matrix. You have been able to find some sort of relation, which you can say that, okay, this is the closed loop transfer function of my system. So this is the way in which your state space representation is really related to what you have already seen as a transfer function. So in transfer function, you saw you took the initial conditions to be 0. See, you have done this here also, just to obtain the transfer function. So you got the transfer function in form of some matrices. Okay. Now we'll move to the questions. Okay. A second order system is governed by this equation. the number of state variables required for representing it in the state representation is. So I just said how do we find what is the number of state variables. So do you remember the number of state variables is defined by what?
Order of differential equation, madam.
Right. Order of the system. So here your order is 2. That means you'll have 2 state variables to define the system. So this is your answer. Okay. So, okay. So this is asking for state matrix for the system. State matrix means A. Yeah. Let me correct over here. It is not system. It is state. State matrix. So this is basically your A. State matrix is given by what? How will solve this? We want to find out A, B, C, every matrix, because in the next questions we'll have what is the input matrix, what is the output matrix. So we need to be solving everything. So what was your differential equation? Y double dot t plus 5y dot t plus 6yt is equal to ut. Okay. So this is some sort of relation between input and output of the system. Now what we'll do, we'll try to get some state variables from here. We are very sure that there would be 2 state variables. Do you want to say something?
Yes, madam. X1 of t is equal to y of t, madam.
Okay.
Right, madam. X1 of t is equal to y of t.
Hmm.
X2 of t is equal to
Is equal to
dy by dt. Y dot.
right.
Then y double dot t is equal to
Hmm.
d square by dt
Yeah,
square.
yeah, yeah.
D square by.
Just a second. I'll make this complete thing over here. 5 y dot t.
Minus 6yt.
Okay. This y dot t
Y
will be
double.
written as x2.
Minus 5 x2 t.
Yeah.
Minus 5 x2 t. Minus 6 x1 t.
x1t ut. And this y double dot t is x2 dot t, right?
Yes, madam.
Yeah. So,
X1 dot t is equal to x2 t, madam.
yeah.
You didn't write. X1 dot t is equal to. Then x1 dot t.
Yeah, yeah, yeah. Just a second. Let me make sure that everyone is understanding. I'll repeat this, whatever is done here. So, see, this was the differential equation that was already given to you. Okay. You're supposed to break it in 2 equations. What we said earlier that we want to have 2 equations. जितने का ऑर्डर है उतने नंबर ऑफ डिफरेंशियल इक्वेशन हमको चाहिए फर्स्ट ऑर्डर के n first order ODEs. Okay. So what you can write? Okay. So it is some differential equation in y. So what I'll do, first variable that I'll define, state variable that I'll define is yt only. Okay. Second state variable, I'll try to take it to be a derivative. क्योंकि डेरिवेटिव लिया तो ये y dot t हो गया. Now I know that if I take the derivative of x2 dot, I'll get y double dot t, which is required over here. Okay. So y dot, so when I try to arrange this equation, this is the same equation arranged. So y double dot t is derivative of this, right? Minus 5 x2 t. X2 was written as dy by dt here. So here you get that minus 6 x1 t plus ut. And since we had x1t to be yt, so if from here you can write x1 dot t to be equal to y dot t, and y dot t from here is x to t only. So basically we get two sets of equations. X1, I'll for just clean solving, I'll remove t. T is everywhere. Assume t to be everywhere. X1 dot is equal to x2, and x2 dot is equal to minus 5x2 minus 6x1 plus u. All right, t is everywhere. It's implicit. Now we want to arrange this in this form. X dot is equal to ax plus bu, y is equal to cx plus du. I want to arrange everything in this form. Okay, so how will
Ma'am,
arrange? Yeah,
I'm actually a bit confused. Can you please explain again?
where exactly are you
Summary.
confused? Do you want me to repeat this process again?
Yes, ma'am.
Okay, okay. So see, I'll how to remove this highlighter. Okay, whatever it is, let it be. So you already saw that this was the differential equation that was given to you, which is given in the first line. Now we want to break this second order differential equation in two ordinary differential equation, first order ODE. अभी सेकेंड ऑर्डर में है, जितना ऑर्डर रहेगा उतने नंबर ऑफ स्टेट वेरिएबल्स आएंगे, और हर स्टेट वेरिएबल के करस्पॉन्डिंग वी आर गोइंग टू हैव a first order ordinary differential equation. All right, so in our case it is two second order, that means two state variables for sure. तो x1 x2 पिक्चर में आना ही है, ठीक है। अभी जब डिसाइड कर लिया कि x1 x2 पिक्चर में आना है, तो उसके बाद let's see x1, so we will try to do something in such a way that y, because y is going to be some output only, तो लेट्स से कि कोई एक जो आउटपुट है वो हमारा स्टेट वेरिएबल ही रहेगा, बिकॉज y would be like how to say that, so in the earlier case y, let's say, was your capacitor voltage. It would be combination of some IR plus Vn, if this whatever was your circuit. So okay, it would be minus IR. So whatever input voltage you have minus the resistance voltage would give you VC. That means that this output, if this is output, it is going to depend on this variable. So it could be minus, let's say, x1 R plus V in. So what I mean is, in our case, since it is second order differential equation and it is not given what is the output, we have assumed that okay, my first state variable is directly the output only by t. So when I wrote, and you'll see the logic why doing this helps. So when you write x1t, the first state variable, to just be the output, you differentiate it, okay? So you'll write x1 dot t is equal to y dot t. ठीक है, अभी यहाँ पे करके छोड़ो, forget this. अभी सेकंड में क्या किया, let's take x2t and let it be the derivative of the first term that we had, because इसमें हमें क्या क्या है, yt है, dy by dt है, और d2y by dt है, dt2 है. Ultimately we have to deal with these quantities only. अगर इसको x1 बोल दिया तो ये x1 डॉट हो जाएगा ऑटोमेटिकली, और इसको अगर x2 भी बोल दिया तो x2 would be equal to x1 dot only. अभी ये x2 dot भी हो गया, तो what we ultimately wanted was x1 dot x2 dot. So let's have some differential equation the number of state variables in such a way that किसी का differentiation तो मेरे y double dot t जैसा हो जाए, ताकि I can write it in some way so that it can be arranged as some like addition or subtraction of the state variables. That is the basic idea. So what we did here is x1 t को yt के जैसा लिया, के बराबर लिया, x1 dot t is equal to y dot t. Now x2 t को dy by dt लिया, which is y dot t. Now you see both of these are equal. That means that x1 t dot t is equal to x2 t. So you get an equation from here itself. So you have some relation between x1 dot and x2, which is of first order only. It is not second order anymore. Now what we do? We write x2t is equal to y dot t, जो देखा हमने. So what you can, so if you write this equation only over here, this one is written here, this equation, ऊपर वाला, it is just rearrangement of the terms. Now y double dot t can be written as x2 dot t. यहाँ पे हमने बोला था कि x2 is equal to y dot. So this can be x2 dot of t is minus 5 y dot t को हमने x2, हाँ, because y dot t was x1 dot t which is x2, तो उसको लिख दिया minus 6 yt को हमने लिखा x1t, right, from here plus ut. So and यहाँ से तो हमने कह ही दिया था कि x1 dot t is equal to x2t. So eventually we end up with these two equations, right? So we want कि हम कुछ तो x1 dot x2 dot should be equal to something into x1 x2 plus something into u. We want to arrange it in this form. If we want to arrange it in this form, we want to get rid of all the y's. The way to get rid of all the y's is कि एक y को ही ले लो एक state, y dot को दूसरा state ले लो. You will have no state anywhere there. अगर ये y double dot की जगह y triple dot होता, ठीक है, हम तीन स्टेट लेते हैं. पहला x1 y लेते, x1 dot would be y dot, which would be also equal to x2. Then x2 dot would be y double dot t and so on. ताकि y triple dot could have been written as x3 dot is equal to something x1 plus something x2 plus something x3 plus u. So just to arrange in this format, we go through this process. Make sense?
Yes, ma'am. Thank you.
Okay. So since we have got this equation, we will try to arrange it in this format. So it is just matrix. Okay. So we'll write x1 dot x2 dot is equal to something into x1 x2 plus something from, acha, there is one more equation which I missed. I missed another equation here, that y here is equal to, from here you can write y is equal to x1. Yeah. So you get the equation of x1 dot is equal to something, y is equal to something. So we want to write it in this way, that x1 dot is equal to something into x1 x2 because of this, plus something into u. Y is equal to something into x1 x2 plus something into u. Okay. Now how we will write this? So see, x1 dot is only dependent on the x2. मतलब ये term 0 and ये term 1. So multiplying this with this would give you the first equation, right? That is why. Now in the second equation, you see minus 6x1 means here would be minus 6. minus 5x2 means here would be minus 5. Okay, in the first equation you had no u, so 0. In the second equation you have u, so it is 1. So this complete thing would give you the total matrix of the system, that how this differential equation was written over here. Okay, now write for y, it would be 1, right? It would be 0. And for u, there would be no u. So this is your equation where this is the A matrix, this is the P matrix, this is your C matrix, this is your D matrix. We have been able to successfully represent a second order differential equation as two different first order ordinary differential equations. X1 dot is equal to something, x2 dot is equal to something. We have been able to do this from here. Okay, so your question had asked what is the state matrix for the system. Now your state matrix is 0, 1, minus 6, minus 5. So this is your answer. If it is taking some time to digest, it's okay, it's perfectly okay, because yeah, it is you have to think somewhat in this sort that how to convert it into two state variable equation and all that. It's completely fine. You'll have so many problems also. If you open up the book of Ogata for modern control engineering, you'll have multiple questions of this sort. You can also practice from Norman and Nice. All of these books have so many questions of this type, and for root locus also you can definitely go to these books, have multiple questions practice. So yeah, this is the way we solve it. If you solve one or two more problems, it would be very easy and very frequent kind of thing for you. Yeah, this is the way we do this. And why we do this? Because we want to get two independent ODEs out of second order differential equation. If it is 3, we want 3 ODEs. Okay, so this was your A, B, C and D matrix here. Your next question is what are the eigenvalues of the state matrix? Before going to eigenvalues, I'll go to the other two questions. I'll come to this again. I'll tell you what are eigenvalues. Yeah, the input vector of the state space realization. What is this asking? This is asking you what is B. What is B here? What had we obtained? It was 0, 1. Right? So does your option have 0, 1? Yeah, it has. So this is your answer. Okay. The next question is the output vector is what? So this essentially asks you what is C. So what was your C here? It is 1, 0. Sorry. Just a second. I hope I made.
Ma'am, your voice is not audible.
Yeah, just a second. Your Y is 1, 0. I think I've written this correctly, na? There is nothing wrong with this. So this is 1 cross 2 matrix. This is 2 cross 1 matrix. You get 1 cross 1. Yeah, Y is equal to, we wanted it to be X1. So this is correct. There is something wrong with this option, I guess. Your answer for C matrix would be 1, 1, 0. Okay. So your
Option B is correct, madam. In row matrix, it is 1 0, but in column matrix, you will write 1 bottom 0.
Yeah, but why would you write it as in column matrix?
Dot product, madam. Nothing but dot product, madam.
So output is no, it is just asking the output vector. So it should be this 1 0 only. It should have this option.
No, madam. In column, if you write it, you will write. You can write in transpose, no, madam.
It is not asking the transpose. So had it asked this C transpose, then it was fine. But it is directly asking me the output vector.
Madam, there is no option, madam, in column row
Yeah,
matrix.
so you should have this as row vector only. So this is very important. P matrix is a column vector, P matrix is always a row vector because you just have one equation for y. Whereas in for states you have multiple x equations, so it is a column vector. It might depend on you. So this is the correct option. It is not present anywhere. So okay. Okay, so another question that I skipped before this was eigenvalues of the state matrix. How do you find the eigenvalues? What are the eigenvalues? For now, you can understand that eigenvalues are equivalent to poles of the system. Okay, so from transfer function characteristic equation, we get poles when we make them equal to 0. From state matrix, you get eigenvalues. Now, why they are called eigenvalues and all, that is a different story. So we'll not go into that. But how we are going to find out, I'll tell you. So what you really do to get eigenvalues is Si minus A determinant is equal to 0. Whereas for characteristic equation you did, characteristic equation is, if it is second order, then it is sum S square plus sum Bs plus C is equal to 0. So this is the way we do. So what was your A over here? It was 0, 1 minus 6 minus 5. 0, 1 minus 6 minus 5. So try to do this. Si minus A. So what is S? Then I is 1, 0, 0, 1 minus 0, 1 minus 6 minus 5. Determinant 0. Do you want to say something, Surya? Okay. So you can write Si minus A determinant is equal to 0. What will happen here then? It would be, let's take the determinant directly. S minus 0. This would be S. This would be minus 1. This would be 6. This would be S plus 5, right? This is equal to 0. Take the determinant. S into S plus 5 plus 6 is equal to 0. S square plus 5s plus 6 is equal to 0. S square plus 2s plus 3s plus 6 is equal to 0. S plus 2 plus 3 S plus 2 is equal to 0. S plus 3 S plus, sorry, S plus 2 is equal to 0. That means S is equal to minus 2 and minus 3. These are your eigenvalues. Okay. So remember this thing. This. Remember this. Si minus A determinant is equal to 0 would give you the eigenvalues. And I'll show you how this gave you the answer. This thing gave you the answer. I'll show this to you. But okay, these are your eigenvalues. Any confusion? And if you know somewhat some method to find out the what to say, the transfer function of the system. Let's say you have been given this, no, A B C D matrix. From here, if you have some method to find the transfer function of the system, you will see that you'll get this characteristic equation only, and you'll be deriving these poles only from there also. Okay, you'll not get some other thing, you'll be having the same answer. So I think we have a question later on in which we want to find out the transfer function corresponding to the same state space equation that you have derived. So yeah, we'll see that. But I hope this is clear. We'll move to the next question. 9 and 10 are already done. We'll move to 11. Yeah, this is the same question. So seeing the last question, you might know what is the answer, but how do we come to it? That is even important, more important. So you remember before this when we were talking, how would you derive ys upon us? So I showed you where that is. Yeah, you remember. I hope you remember this thing. This. I told you that this is the way in which we find out the relation between ys and us, right? So we took the Laplace of the system that we had. We took the Laplace of the output that we had. We substituted the value of x's in the output equation to get what is the relation between ys and us. Okay, and this your ps over here. So sorry, I moved to the next question. Okay, so ys upon us. Now what I want to do is I want to sorry I want to find out C Si minus A inverse B plus D. You might have noted what is A, what is B, what is C, I assume, so that you are able to find this. I want an answer to this question, please, where you make the calculations. If you, okay, your C is 1, comma 0 row vector. Please note it down if you haven't. Your B is a column vector 0, comma 1. And your A is a square matrix 0, 1, minus 6, minus 5. All right. Just make these calculations. Taking the inverse would not be so tough because it is just a 2 by 2 matrix. So please try to find out an answer. I'll write some steps for you. C is 1, comma 0. Then S 0, 0, S. This is your Si minus A. What is your A? 0, 1, minus 6, minus 5. Want to take the inverse of this whole thing into B. B is 0, 1 plus D. D is already 0. Solve this to tell me what is the transfer function you obtain. Do you get this to be the answer? Guys, come on. Did you solve? You should have the option A as the answer. It is just taking the inverse of a 2 cross 2 matrix. Not that tough. The terms in C and B matrices are also, one of the terms is 0. It would just simplify your multiplication to such an extent that you would just obtain 1 cross 1 value.
Yes, ma'am.
Okay, good. So, yeah. So we already saw that from these calculation, Si minus A determinant is equal to 0, gave you some eigenvalues. And here you saw that this was the characteristic equation obtained. The same characteristic equation you are getting from here also when you're trying to convert this uh, the differential equation, the second order different, the two first order ODEs to transfer function. You're getting the same transfer function and the same characteristic equation. So from here, if you say what are the poles of the system, you'll say it is minus 2 and minus 3. So you've got literally the same answer. So both of them are equivalent. That is why. All right. So this is the way you go from Laplace domain to state space domain, and from state space to Laplace. So this is the way you're supposed to follow. You always might have questions of this way, of this sort, where you're supposed to find out that what is the relation between like how do you go from one domain to other and perform some calculation. For example, you have the state space equation over here, and you are supposed to find out what is the rise time or maximum peak overshoot. What would you do? You would go for from this A, B, C, D, the state space representation, to Laplace domain, because zeta and omega n are defined in that way only for second order differential for second order system. You would go to Laplace domain, compare the omega and zeta, and then try to find out, okay, this is my peak overshoot. So that is one of the ways. Okay. Now, why is this happening? It is not stable. Yeah. Okay, so you already saw in your lecture also, I'm just revising this, that what is the frequency response? So it deals with the response of the system when a sinusoidal input is provided. So you saw ys upon us to be some transfer function. Let's say your ys is equal to ps into us. Let's say your ut is now some sinusoidal function. Then your us is some sinusoidal in Laplace domain. So if you're going to find out everything, you'll find this to be answer, where there is some scaling of the sinusoidal wave. So it would be like this way. U naught of pj omega is given over here and it is shifted in phase. So the steady state output is a sinusoidal signal of the same frequency as that of the input. You see, the frequency is same, this omega is same, but scaled in magnitude. So it is scaled in magnitude by pj omega and shifted in phase by phi. So this is the phase shift and this is the scaling. So this is scaled in magnitude and shifted in phase. So yeah. The question that we have here is, so the frequency remains minded. The frequency remains the same. The phase is shifted and the magnitude is scaled. Scaled in magnitude, shifted in phase, but no change in frequency. So if you are given this question, when you have an LTI system that is provided with a sinusoidal input having a frequency of 12 Hz. So you are providing a sinusoidal input with a frequency of 12 Hz. Then the corresponding steady state output would be a sinusoid having a frequency of what?
12 hertz, madam.
Right, 12 Hz. Because you're going to have the same frequency on input and output if a sinusoidal wave is given as an input to the system. So this is conceptual question. You don't have to perform any calculation over here, just use what was taught. Okay, so this is again a very simple question. You know how to play with complex numbers. So we'll solve this. So the transfer function of plant is this one. The magnitude at an angular frequency of this is what? So let's convert it into j omega format. Okay. So your transfer function is what? S plus 2 upon s plus 4. We can write it as 2 plus j omega upon 4 plus j omega, right? Now, what I want to do, I want to find out the magnitude. If I want to find out the magnitude, I definitely have to get rid of j term. So how we'll do? पहले conjugate निकाल देते हैं. Just to in the next question we are supposed to find out the phase of the system. So from here also you can calculate the magnitude by squaring the numerator and denominator independently. But in the next question we'll try to find out the phase. So I'll simplify it to such an extent that we can find the phase easily. So basically I'll try that there is no imaginary term in the denominator. So it is 2 plus j omega 4 minus j omega upon 4 plus j omega into 4 minus j omega. I have multiplied by the conjugate of the denominator in both numerator and denominator. Now, it would be 8 plus omega square plus 2j omega. Please check. This should be correct. I hope everyone agrees. Divided by 16 plus omega square. So this is the thing we have done. Now we want to find the magnitude. Before finding out the magnitude, I'll put frequency to be 1 radian per second. So I'll write at 1 radian per second. Transfer function at omega equal to 1 is 8 plus 1 is 9 plus 2j upon 17. Okay. Find out the magnitude. I'm trying to find the magnitude. It is 81 plus 4 upon 17. What is the answer?
Zero 0.54.
Sorry, what is the answer?
0.54, ma'am.
Right. Very good. It is 0.54. So this is the way in which you can find out what is the magnitude of the sinusoidal function. Now for the same question, I'll copy this part before I move there. So I want to find the phase for the same frequency. So my transfer function was transfer function was this, right? Now, if I want to find the phase, then what I'll do? Phase of transfer function at omega equal to 1 is, so this can be written as 9 upon 2j upon 16 plus omega square. It is tan inverse 2 upon 9. What is tan inverse 2 upon 9?
$12.53.
Very good. It is 12.53 degrees. Okay. So this is the way in which we find out the angle. All of you,
What about the denominator?
sorry?
No,
Denominator.
denominator.
Yeah, so see now, what would happen here is tan inverse 2 upon 16 plus omega square, right? Upon 9 upon 16 plus omega square. So this would eventually cancel, right? And you'll have tan inverse 2 upon 9 only.
Yes,
Okay.
understood.
Okay. So in the same question, what is the ratio of sinusoidal function at an angular frequency of 10 radian per second to that of 1 radian? Basically, whatever you did here, you're supposed to do the same thing with omega is equal to 10 and find a ratio. It is easy only. So your transfer function was this is your transfer function. Now transfer function at omega is equal to 10 radian per second. Magnitude is equal to 8 plus 10 square, which is 108 plus omega is 10, so it is 20j upon 116. When you try to find out the magnitude, you can calculate it to be 108 ka square plus 20 ka square upon 116. You'll get some magnitude over here. Can you tell me what is the number you're getting?
$0.946, ma'am.
0.946. Okay. So we are supposed to find out the ratio. So what is the ratio? Ratio is transfer function um, omega at 10 radian per second upon transfer function, sorry, transfer function at omega equal to 1 radian per second magnitudes ratio. Means I'll take it to be 0.95. 0.95 upon 0.54. So you'll get it approximately equal to 1.75. So this is your answer. Okay. So these questions were really easy. The conceptual question that you had was in 12 hours. You would have understood by now what are the state space representations of the system. So all these questions are the new ones for you. Rest all you need by yourself.
Hello, madam.
Okay. With this, we end the today's lecture.
Hello, madam.
Yeah, and the next class will be dealing with probably yeah, you'll have the Nyquist stability criteria and all, so we'll see that. Yeah, Surya.
Madam, calculator is allowed, madam, or you will have digital calculator, madam.
Uh, can you ask this question in the portal itself?
Okay,
I am
madam.
not aware of this, so please raise the question over there.
Yes, madam.
Okay, I'll stop the recording.